Welcome to Sustainability Modeling Lecture number 6, Modeling Population Nature Interactions. The cartoon on the left relates to one of the cases that we are going to be covering in today's material.
Let me tell you about the contents of this lecture. We're going to be reviewing system dynamics models that involve the interaction between population and either enabling or limiting resources, and mostly we're going to be focusing on natural resources. So these are, last time we spoke about when one population enabled or limited the others through competition. Today we're going to be looking at natural resources and their interaction and how they limit or enable population. We're going to be doing this through 3 case studies. One that has to do with the Kaibab Plateau in northern Arizona. The other one, which has to do with the Maya collapse of the population of the Mayan over 1,000 years ago, and then we're going to be focusing on a general population nature model formulation that we're going to be using later on in the class. So I'm going to jump right in and talk about the first case study, which is the Kaibab Plateau, and this is located in northern Arizona. It's a large, pretty flat area of land that's it's just north of the Grand Canyon, and I'll show you a map. At the beginning of the 20th century, the U.S. government created the Grand Canyon National Game Preserve, and that preserve included this Kaibab Plateau. And when they created the reserve, deer hunting became prohibited, and not only that, but at the same time, there was a bounty that was established to encourage hunting of pumas and other natural predators of deer. For example, in 1910, nearly 500 pumas were trapped or shot. And so this is a little map of where, so this is the Grand Canyon National Park in north central Arizona. So the Kaibab Plateau is just north of that, and nearing the border with Utah. And this is a little picture of the plateau today, looking north, looking south. So you can see a little bit of the landscape. So I just thought I'd show that. Now let me tell you about deer in the Kaibab Plateau. And when the predators of the deer were taken away, particularly the pumas and other predators, the deer population actually began to grow quite rapidly. And so deer herd increased from about 5,000 in 1907 to nearly 10 times that in about 15 years. So it really took off, and now over the winters, sometime between 1924 and 1925, nearly 60% of the deer population died, and so it was a sudden collapse of the population, and actually continued to decline over the next 15 years until it finally stabilized at about 10,000 in 1940. So this is a good case to look at how population grows and then declines very rapidly and then stabilizes. And we're going to be looking at a Vensim model for this. I wanted to walk you through the essentials of how the model is structured, and we're going to be looking later in this class, in this lecture, specifically at how how the model works. But let me tell you a little bit of how the model is structured. It's got 2 stocks. It's got the deer population, and the limiting resource in this case is food. Okay, food that's available in the plateau. The deer population is driven by a growth rate on the plus side and the predation rate on the negative side. If we look at the plus side of the source of deer, deer reproduce themselves, so there's a sort of the growth rate factor that is driven by food, and I'm going to get back to that in a second. And so that's the plus side of deer. The negative side of deer is predation, and this model that I'll show you has an exogenous predator population. That means that the predators are sort of specified externally. They're not a population modeled explicitly. So there's we'll see we'll see the reason for that in a minute. Now the predation rate is driven by not only the predator population, the presence of predators, but also the availability of deer. Expresses a deer density, which is driven by the population and the area of the reserve. Okay. Now let me get back to the food issue, because food drives growth of deer. Food is also a stock, so it's got an in and an out. The way food grows, it's a natural preserve, so there's an ability for vegetation and other food sources of deer to regenerate naturally, so there's a capacity in the reserve to generate food, and that's how the source of food gets into the picture. Then the consumption, the negative side of food, is the consumption by deer, which is of course driven by the deer population, and that's that's how the cycle works. So deer is the population, food is the resource. The food, it gets consumed by the deer, so there's a feedback loop there, and food has a natural ability to regenerate, and that food generation actually drives deer growth. So that's another feedback that's there. Okay, so we're going to be looking at this model and their parameters and some specific results later in the video, but I do want to show you some key results. So with this model structure, you can actually plot the population of deer, and that's what's in this graph. It's the population of deer for a period of 50 years between the beginning of the 20th century and the mid 20th century, which is about the time where the deer population is established. And you can see what happened. The deers were fairly stable until in 1910. Around this year, the predators of deer were taken out. So the pumas were taken away, and the deer population started growing very rapidly. Then all of a sudden, mid-1920s, they collapsed very quickly over the period of a couple of years. They went away, and then finally sort of bounced back and stabilized, in the 40s and 50s. So this is a little bit of the result of that feedback. Okay, and I'll show you how the model is structured. You can also see the other stock, which is the food. Again, very stable until circa 1910, when the deer start growing very rapidly. Food starts getting depleted very quickly, and you can see why the deer collapsed, because they essentially ran out of food. Eventually, the food itself, because the deer sort of stabilized and bounced back, so did the food, and it stabilized. So this stock as well follows this pattern of sort of collapse and then bounce back and stabilization, and that's typical dynamic behavior when you apparently there was a limit that was overshot by the deer, and then it brought the system into a collapse, but then it sort of came back. And we're going to be looking at why that came about. We can summarize the results of this case study as follows. First, the elimination of the puma, which was the predator, enabled the rapid growth of the deer after 1910. And this growth decreased the food supply faster than it could be regenerated naturally. So this basically created this overshoot that resulted in starvation of the deer. So this is an assignment for you. I want to ask you what has happened with deer in the Kaibab Plateau since 1950, and how would you update and or use a model like this? And I'd like you to think about this, to do a little bit of research, and to post your feedback on our thread, on our Facebook page. Okay, so this is an assignment for you. So that's going to be a key assignment for discussion. There's some suggested reading that you can take a look at, and you can learn a little bit more about the Kaibab Plateau and the history, and this will give you some hints as to what has happened since 1950 that you can use to explore how would you modify the model. Okay, so I'm going to let you read those things. Let me move on to the next case, which is also very interesting. It's the collapse of the Maya. You may be familiar or somewhat familiar with the Maya. This civilization collapsed at about roughly about a little bit over 1,000 years ago. It was probably the most advanced native civilization in what today are the Americas. Before European arrival in the 1400s and in the late 1400s, early 1500s. And what's interesting about this collapse, and if you read about it, and there's a couple of readings I'll suggest, it's a little bit of a mystery. There's been several explanations that have been proposed, but because there was very little evidence, it's been difficult to prove any of these theories. What's interesting about this collapse is that it resulted in a completely depopulated location that remained so depopulated for the next 800, 900 years. So literally, this population of over 2 million people, it was estimated at the time, was completely wiped out. And it didn't really, the same area was completely depopulated for another 800, 900 years. So it's really, there was no evidence, no remnants that you can look at, human remnants that you can look at. And so a lot of scientists are trying to put the puzzle together. And so here I want to explore this issue using system dynamics modeling. And this is a little bit of a geographical area we're talking about. So this is the sort of the southern part of Mexico, including the Yucatan Peninsula and portions of Belize, actually all of Belize, Guatemala, portions of Honduras and El Salvador and Nicaragua. So it was a fairly large region, and this is a little schematic. The majority of the Maya ruins are in the northern area. But they've been uncovered slowly in other parts of the region as well. And here's a little comparison between two major civilizations: the Mayas, which inhabited this portion of Central America and Mexico, and the Aztecs, which actually did not go through the same collapse. Okay, even being nearby. This is a little clip of a paper, New York Times, back in 1979, and it's an interesting read. At this point in time, one study came about that sort of highlighted one of the reasons that the Mayas could have collapsed was because of abuse of their surrounding environment. And since the late 1970s, so through the 80s, 90s, and last decade, there's been a series of studies that sort of have slowly been showing evidence of this, and I'll show you a little bit of that. But there have been several explanations over time of why the Maya collapsed. Foreign invasion was one of them, and this was sort of discarded. It's been discarded based on the fact that no one populated that area for the next 800, 900 years. So it did seem odd that it will be invaded and not be occupied. Some sort of internal social turmoil, revolution. But again, this would have left at least the winning party somewhat empowered there. That didn't quite happen. Collapse of trade routes. The Mayas were, given the density of population that has been estimated, it's been hypothesized that the Mayas had fairly sophisticated commercial practices, and now there's two practices that have been mentioned: trade and agriculture. And I think the trend has gone more towards agriculture. So this, again, because if there's a collapse of the trade routes, you would think that even though if those were away, that there would be some remnants, and that hasn't happened. And there's a reading that speaks about this in the that I'll assign. An epidemic, and that's always there's always a possibility that an epidemic could have wiped the population out. However, there hasn't been a whole lot of evidence of that. Climate change, and particularly droughts, and again this issue of abuse of environmental resources, particularly soil and water through agriculture, and the majority of the studies and evidence points to some combination of climate and environment and abuse of environmental resources, which all fall under the general environmental issue of this interaction between the Mayas and their surrounding environment. This is one study that suggests that indeed there was around the time of the Maya collapse, there was a combination of environmental factors that could have driven to their demise. And what's shown here is it's an age. So this is 0 is present, and these are years before present here in thousands. And about 1,100 years ago, there was a big spike in sulfur content and oxygen isotopes in the sediments that in the soils that were there at the time. And this is suggestive of a couple of things. One of a sudden shift towards a drier climate, and if the Mayas indeed relied on agriculture, this would certainly explain a very quick decrease in agricultural production that could generate a collapse in population. So it could have been a combination of things. It could have been a drought and essentially an inability to grow food through agriculture. So this is the attempt to capture some of these factors in a Vensim model, and I'm going to look at the Vensim model from the bottom up here, where we have the population stock, okay, and population again, like all models of population we've been seeing, have a natural increase rate due to births, and then here there is a decrease in population due to immigration. So this natural increase should be interpreted as a net. So these are births and deaths, and then the outs here in this model, in this particular model, are from people leaving. Okay, just emigrating for in this case for lack of food. So I could have just put another arrow going out for deaths, and that would have been fine. So that's okay. It's just a matter of simplifying the model and trying to differentiate your births and deaths from actual migration. So population is driven by food consumption, and so the population creates a demand for food. Okay, and this availability of food may drive migration. Now let's see where this food comes from. Okay, the Mayas converted forests, which is one of the stocks in this model, to lands. Okay, they did deforestation, and they converted forests to lands for agricultural production. Now, these lands produce food. We're able to produce food, and the fertility of the lands can be, if the lands are intensively worked on, like is suggested to be the case, because the Mayas was a large population. At the height of their demise, it's estimated there were 2 million people in that area. So that's a heavily, for that period of time, was a very densely populated region. So let's take a look at how this flows. Essentially, forests get converted to lands through deforestation. Okay, these lands are able to produce food. Okay, and these lands also, over time, lose fertility. Okay, and the fertility of the lands then drives even more deforestation, because as the lands become less fertile and less productive, there's more forest that comes into play, and there are evidences that there's evidence that the the amount of deforested area was increasing over time. Okay, so when food gets produced, this generates a gap between what's demanded of the existing population and what's actually being able to produce by the lands. Okay, so that's how the feedback works, and so this generates an interesting dynamic in which population grows, limited by food availability. So that's the limiting resource. In this case, it's food, but indirectly it's a natural resource like forest that gets transformed to land to produce the food. Okay? And that generates this dynamic of the feedback dynamic. So we're going to go when we look at the Vensim model in detail. Within Vensim, we'll see specifically how this model was parameterized, but I'll show you some of the results that came about with this model. Also you can see that and these are years. Negative means essentially before Christ, and then positives means after Christ's death. So these are years BC negative and years AD positive, and you can see that the collapse occurred here at about 1,000, and you can see that about 1,000 years BC, the population started growing very rapidly, and you can see this typical exponential growth that we've discussed. Then it reaches sort of a point where all of a sudden it collapsed very quickly, and then it really never recovered. So that's essentially the result, the outcome of that model. We're going to be looking at this in more detail. But you can also look at the other stocks, the forest, and follow. They followed similar. In this case, this was about the extent of forest that was available to them at the time, and this is what essentially came of it. And this here, at about the same time, collapsed. And you can see the fertility of the lands, which was another of the variables in the model. Collapsing from 5 million kilograms of food per square kilometer of area per year to 0. And here you can see in this plot, you can see the 3 variables plotted, and we discussed last time how this was how this was done. Okay, so we're going to be looking at this later on as well. Here's some suggested reading. There's a chapter 5 in the book Collapse by Jared Diamond, which I think has a very nice portrayal and a little bit of a historical perspective. And there's a couple of other readings that I want you to do are online. And I have another assignment for you. I want you to look at the Vensim model and vary the parameters and see. I want to see some insights as to. And I'd like to see you play the model, and whatever you come up with, I want to see some postings on our discussion page. Okay, it'll be fun, I promise. The third model that I want to look at today, it's a little bit more theoretical, but I want to lay the basis for some more sophisticated models that we're going to be looking at in this class. This is a model of population and nature interactions, and it has 2 stocks, population and nature, so let's keep them simple. The premise is that population consumes natural resources, while natural resource availability drives the mortality rate of population through a feedback. Nature can regenerate, and it has an upper bound to this regeneration given what we're going to be calling the system's natural capital. So there's a natural capital, and you can actually research this term. It's a term that's used to embody the availability of nature to provide for humans and other populations. So this is a little bit of the schematic of the model we're going to be discussing. There's 2 stocks, population and nature. Okay, population has birth and deaths. Okay, and the births are driven by a birth rate. The deaths are driven by the availability of nature. So there's a nature per capita variable that it's found by essentially a ratio of the nature to the population, and that drives the death rate of the population. And there's I'll show you what these are, but these are essentially some parameters that appear, which result in an alpha death rate. Nature, on the other hand, can get regenerated because nature reproduces, vegetation reproduces, and other resources get replenished. But that is limited by a sort of upper bound, which is natural capital. So nature gets regenerated, nature gets depleted by the population, and that's where the feedback comes in. So it's a very simple, a two-stalk with feedback model. And let's take a look at the equations. So you have two populations, X and Y. Population X, that's a growth rate, beta, and a death rate, alpha. Okay. Nature follows a little bit of a logistical equation where nature gets regenerated with an upper limit given by this natural capital, K, and nature gets consumed, delta, and the consumption is proportional to the population. Okay, so that's essentially, it's very simple, two-variable logistical model. I don't want to get too hung up on the math, but I just want to show you what the equations look like. Let me tell you essentially a little bit more about how this model is formulated, and this is the link between nature and population mortality. So the alpha, which is the death rate of population, it's essentially driven by the ratio of nature availability per capita. And this basically means that if this ratio is large, that means, so if you're on this side of the graph, it means that you have plenty of nature per person, and then the death rate is a minimum. It's essentially a natural birth rate, but nature has very little impact on the death rate. But however, as you start moving to the left part of the graph, and essentially you start having less and less nature availability per person, and that could be because you start running low on nature or because you have too many people. So if you start migrating towards the left part of this graph, you'll reach a point where then the mortality starts increasing because you have less availability of resources for nature. Okay. Now we parameterize this model. I'll show you that in Vensim, and then you can see a couple of things. Here's a graph of population and nature. Population is given in blue, in the blue line, and it's people. Okay, and in this particular case, this is the scale of people, and nature is given in the funny unit. We're going to call them ecological dollars, or just to measure it as capital. Okay, and in this case, the simulation started high on nature, and then nature, as population came down, and when it started coming down because population was growing, then population reached the maximum, and then population starts crashing. So does nature, but eventually, both of them sort of bounce back and stabilize, and essentially you reach in a similar way. This was run for 500 years with these parameters. You essentially reach a sustainable situation in which this amount of population is able to exist within this amount of nature. Okay, so I think the morale of the story is that there are ways to manage natural resources and population that allow sustainability sustainability to be achieved. Okay. And here's the associated death rate with that simulation, and we'll look at this again in Vensim, and you can see again that the mortality started low, then it grew fast because you start running out of resources, and then it sort of bounced back, and then it stabilized at some value. Okay, some intermediate value between the minimum and the maximum. So here are some of the key results of this lecture. First one is that the population-nature system can be sustainable over time. So even though there are trade-offs and even though there's interactions between the two, the system as a whole can reach a sustainable limit. I think the second result is that both population and nature stocks do reach steady state conditions below their initial values. So the system reaches a sustainable steady state, and it does so below their initial values, which means that their initial values will overshoot. So at that level, the system would not be sustainable. So here's an assignment for you. I want you to look at the models and the model parameters and vary them and play around with them. I want you to push the models and try to see what you get, and to post your results on a thread on our discussion page. Actually, post graphs as well. Even better if you do that. You can watch the model videos for the 3 Vensim models that we developed in this class, and there'll be individual videos for those, but you can actually watch them here on YouTube. So that's it for the lecture. Thanks very much.